Transformers and Power Lines by Jack,
Eduardo.
Oscar, and Mo.
So what are power lines? Power lines are conductors, usually overhead wires or underground cables that carry electrical energy from one location to another, typically power plants, to homes, schools, and businesses. Their purpose is to carry electricity over long distances and to deliver power from generation sources to consumers. There's two types of power lines, transmission lines and distribution lines. Transmission lines carry high voltage electricity across long distances, and distribution lines carry low voltage electricity from substations to individual consumers. And they're usually made from aluminum or copper for high conductivity and are supported by utility poles or steel towers.
The different types of power lines. Okay, so we have the transmission lines and we have the distribution lines. For the transmission lines, for the voltage level, so the voltage level is very high, typically varies from 69 kilovolts to 765 kilovolts. And then when it comes to the structure, they're mainly large towers spaced far apart. And then when it comes to the distance, they're designed for long distances transmission across cities, states, or regions. For example, the big metal towers you see along the highway or rural areas. The distribution line for the voltage level, lower voltage, they're typically from 120 volts to 25 kilovolts. And then the structure of the distribution line, they're smaller, they're mainly wooden or metal poles often seen along streets. For the distance, they're mainly used for short distances within neighborhoods or towns. For example, the power lines you see on streets near houses and businesses.
So the next thing that we're going to talk about is the components of power lines. So the primary line is what brings the high voltages from the substation to transformer, and then that brings the voltage over to residential areas. Then we have the neutral line, which brings any excess voltage over back to the source, which is the substation. And then we have the pole ground wire, which provides a ground source to disperse any hazardous voltage that could harm the equipment. And then we have the transformer, which lowers the voltage for residential use, specifically a step-down transformer. And then we have the secondary service drop, which explains how the transformer is able to lower the power for commercial use. And then we have the lightning arrestor, which is sort of like, which sort of ensures that the equipment does not get damaged in an event like lightning were to strike it. And this is due to a gap of air, which is separate from the ground wire and the live wire. And then we have the cross arm, which holds up the wires because you don't want the wires drooping near the earth, as earth is the ground and it grounds any charges. Then we have the guy wire, which helps stabilizes the utility poles. And then lastly, we have the insulators, which is used where the live element, which is the wire, and a non-insulated surface could interact, meaning we don't want them to intermingle.
Transformers are electrical components which transfer an electrical signal from one circuit to another while transforming the current, voltage, and impedance. They do this by using two electrically isolated coils and operate on Faraday's principle of mutual induction, in which an EMF is induced in the transformer's secondary coil by the magnetic flux generated by the voltages and currents flowing in the primary coil winding.
Alright, so how distribution transformer work? So when transferring power from distribution lines to actual homes and buildings, a distribution transformer is needed to decrease the voltage to a usable voltage for the appliances that you're using. This is done with a step-down transformer, which has a smaller amount of coils on the output than the input side. Based on which side has more or less coils determines if the transformer will step the voltage up or down. With more coils on the input side than the output, the voltage will be decreased and the current will increase.
This is a simple circuit diagram for how the power is transferred from the power station to the actual home. It starts as an AC voltage source, which is then brought to the substation, which has a step-up transformer, On this one, the input has less coils than the output, therefore making the voltage higher and the current lower. This then moves to the transmission wires, which then would run off through utility poles to the actual homes. In this one, for example, it goes firstly to a fuse, just to ensure that no overloading can mess with the system, so the fuse will trip in case that happens. And then this moves to a step-down transformer, which has more coils on the input than the output, causing the voltage to increase, the current to increase, and make the voltage around 120 to 240 volts, which is used for homes and appliances. And then over here is just the load, which is the homes themselves. Next, we looked at a couple of the equations from the latest video on how transformers work. For a step-down transformer in particular, we want a smaller amount of coils on the input than the output. We also looked at the voltage equation, which says that the voltage output is equal to the number of coils for the output over the input, multiply the voltage of the input. We rearranged this equation just to look at what the coil ratio would be based on the regular voltages in power lines and homes. We rearranged it to have it be so the input voltage of 7,200 is equal to the output voltage of 240 volts over the number of coils output over input. Just solving this gives us that the number of coils for the output over the input is equal to 0.033, which means that for every coil in the input, there is 0.33 coils in the output. So let's say there's 1,000 coils in the input, there will only be 33 coils in the output to give us the voltage we want.
All right, lastly, what have we learned? We've learned three main principles: how electricity reaches our homes, and that is through high voltage being transmitted and then reduced by transformers before entering our homes so that it is usable as so that's able to be used in our daily lives. Why high voltage is used for transmission, and this is to reduce energy loss. And since power loss is calculated by the product of resistance times the quantity of current squared, meaning that lower the current, the better. And so transformers make this possible by converting low voltage, high current electricity into high voltage, low current electricity for long distance transmission. And lastly, transformers are critical for efficiency, and this is done so that the power grid is efficient, and the transformers do this by switching the voltage and current level to ensure that there is minimal power loss.
This is our works cited, and thank you very much.